Hello friends, so far we have discussed the construction of green function for homogeneous boundary condition with homogeneous boundary value problem with homogeneous boundary conditions. Let us consider this non-homogeneous equation px y double dash plus p dash x y dash plus qx yx equal to f of x. If you look at carefully, this equation is given in terms of self-adjoint form. So this is a self-adjoint equation, and boundary condition also given as v1y and v2y, and v1y is defined at the point x equal to a, and v2y is specified at the point y x equal to b. And here we have assumed that this v1 and v2 both are linearly independent. Also we have assumed that we have two linearly independent solution of the homogeneous problem, that is Ly equal to 0, such that the first solution y1 satisfy the condition given at point x equal to a, and the second solution y2 satisfy the boundary condition defined at x equal to b. And now with the help of this, now we have this result which says that if gxi is a green function of the homogeneous boundary value problem Ly equal to 0 with the boundary condition v1y equal to 0 and v2y equal to 0, then yx is a solution of the non-homogeneous boundary value problem 1 and 2, means this problem. So this is Ly equal to f problem if and only if yx is given by this expression a to b gxi f of xi dxi, where here your gxi is the green function of this homogeneous boundary value problem. If you look at carefully, this we have constructed in previous lecture. So if you remember here, this y1x is the solution of the problem Ly equal to Ly equal to 0 and satisfying the boundary condition specified at the point x equal to a. Similarly, y2x is a solution of the problem Ly equal to 0 which satisfy the boundary condition specified at x equal to b. And for our calculation purpose, we have assumed that this is denoted as g1xi and this is denoted as z2xi. And here the term in denominator, that is p xi w xi, this is basically a constant and it is independent of xi and x, that we can prove by this result. So if you remember, we have already discussed the Green's formula for this self-adjoint operator. So if we take the operator Ly, which is defined as this self-adjoint form, then we can define our Green's formula which is between a to x, and it is given by vlu minus ulv dx equal to this quantity. Now here if we take two u and v are two function of the homogeneous problem, that is lu equal to lv equal to 0, then if you put it u and v here as a solution of operator L, then this term becomes 0. So v into 0 minus u into 0, that becomes 0. So this implies that this expression is basically 0, and if you look at this expression, we can say that px minus times w of x is equal to p of a minus times w of a, or I can say this is that px wx equal to p of a w of a, and since a is a fixed point we are taking, so this is a constant value, and x we can take any arbitrary point in this interval. So we can say that this quantity px into wx is always remain constant. So using this expression this result that px wx is constant, we can write it yx as this. Here y of x we have split it into two interval, a to x and x to b. So here between a to x, gxi f xi dxi is given by y2x y1 xi divided by this a, where it is defined as p xi w xi, but since we already know that p xi w xi is a constant, so we can write it some value a. So we are here we are assuming this a is denoting this constant value. So between a to x we have written gxi equal to y2x y1 xi, and between x to b gxi is written as y2 xi y1x. Now here we want to show that this actually this actually satisfies the differential equation, non-homogeneous differential equation. For that we need to say that this yx satisfies the non-homogeneous boundary value problem. So for that we simply calculate the derivative of this. So let us calculate the derivative here, y dash x equal to this quantity. Here we are using the Leibniz formula for differentiation under the sign of integration. I'm just going to write that formula here. So if we write ax bx, here we have kx xi, your phi xi d xi, and if we differentiate with respect to say d of with respect to x, I can write it here as ax b of x, and differentiation of this with respect to x xi phi of xi d xi, plus now take the upper limit, say bx. So you take x in place of xi, in place of the variable integration variable you put this bx. So b of x here, phi of b of x here, and the differentiation of this b dash x minus, and now in place of xi you can write out the lower limit x a of x phi of a of x and a dash x. Here we are assuming that this kxi, phi xi and limit ax and bx all are continuous function with respect to x. So this is the formula which we are using to find out y dash x, because if you look at using this formula, let me write it here. This is y of x. Just quickly I want to write it here. So y of x is equal to 1 upon a to xi, and here we have y2 x and y1 xi f xi d xi. I will write only for okay, plus 1 upon a. Similarly you can write it xi to b and y1 x y2 xi f xi d xi. I'm going to write only for this, rest you can say. So it is 1 upon a. Now if you look at this term, simply say that between a to xi, since we have only this term for x, so we simply write it y2 dash x y1 xi f of xi d xi, plus so there is no other term for x, so we have differentiated only with this y2x, plus if you look at this term, then here the upper limit is xi, then if you can put here, but when you take the derivative of upper limit, that is going to be 0. Sorry, here I think it is x not xi, so let me please sorry, this is x not xi. So if you take here this thing, and if you take the derivative of this, that is coming out to be 1. And if you look at this term, then we have say y2x y1 x here lower limit is a, so I'm writing xi as a, so we simply write y1 a and f of a, and if you find out say derivative of a with respect to x, so that is going to be 0 here. So here this term is simply vanish and we have only this term left, and similarly if we do it here, we will get 1 upon a, here it is x to b y1 x, now derivative of this means y1 dash x y2 xi f of xi d xi, plus use this term. If you take this term, then upper limit is b constant, so this upper limit will simply vanish, so we'll consider only this lower limit, so that is 0 here, minus I will write it here 1 upon a, I think I have left here a, so this a here 1 upon a, I'm writing here y1 x y2 x and f of x, and here it is x here. So derivative of x is simply 1. It is this. This is, please correct this also, this is x. Okay. Is it okay here? Yeah. So between a to x we differentiated this using this same formula and we are getting this. Now if you look at this quantity is same as this quantity. Here basically it is at xi equal to x. So I am putting xi equal to x here. So this quantity will cancel each other and we have y dash x defined as 9. So here we have seen that this y dash x is given by this thing. So y dash x is given by this. This will cancel out and y dash x is given by this. And you can say that it is given by this formula 9. So y dash x is given by this. Using the same formula you can define y double dash x and this now here the boundary condition. So when you take this term here when you consider the upper limit and here the lower limit and using the jump discontinuity of Green's function, it is coming out to be this quantity, that y double dash x is equal to fx into wx Wronskian of x divided by a plus this quantity. Now once we have your y of x, y dash x, y double dash x, then we can form this expression Ly, which is px y double dash x plus p dash x y dash x plus q of x y of x, and we can calculate, and this quantity Lyx is coming out to be this, and this is nothing but your f of x. Here so it means that if your g is given by expression 6, then the yx equal to a to b gx xi f of xi d xi will satisfy the non-homogeneous problem given by this Ly equal to f of x. The only remaining thing left is that it also satisfies the boundary conditions specified at point A and B. So for this you look at this equation, equation number 9, and if you put x equal to a, then this integral will simply vanish and it is a to b y1 dash a y2 xi f of xi d xi. So I can take y1 dash xi out and I can write expression as y of a y dash a equal to 1 upon a y1 dash a equal to y1 dash a to b y2 xi f of xi d xi. Similarly you can use equation number 8 and put x equal to a, this term integral will vanish, and here it is a to b y2 y1x you can take it out, and y1a basically will be taken out, and a to b y2 xi f of xi d xi. So it means we are getting this y small a is equal to this and y dash a. So basically ya whatever condition y1a satisfy, the homogeneous condition y1a satisfy, the same boundary condition will be satisfied by this function y of a. So this follows that y satisfies the same homogeneous condition at x equal to a as the function y1. Similarly we can do the things for point x equal to b. So now looking at the converse part, we want to show that this differential equation 1 along with the associated boundary condition will give you the expression yx equal to a to b gx xi f of xi d xi. For that we consider simply if you look at here, f of x equal to Lyx, right, and then what we do, we simply multiply by g of xi here as gxi, and then integrate between a to b. So a to b gxi f of x dx is equal to a to b gxi y of x d of x. So it means that we are getting this expression that a to b gxi f of x dx. Now here we again truncate this interval a to b into a to xi and xi to b, and between a to xi this g is given by, let me go to this, between a to xi your g is nothing but g1 xi. Similarly between xi to b gxi is given as z2 xi. So using this expression 6 we can write it a to b gx xi fx dx as sum of these two integral. Now with the now we want to show that this is nothing but your y of xi here. So for that we use our Green's formula between a to xi. So a to xi g1 xi ly x d of x. If you use this, it is nothing but p xi g1 xi 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 y dash xi minus this p xi is outside the entire bracket and this thing. So we are just using the Green's formula for v equal to g1 xi and u equal to y. So the same formula we can apply for the second one for xi to be g2 xi ly x d of x. So here this will be given like this. So using Green's formula we can write it like this. If we sum these two, if we use this expression given in 11 and the expression given in 10 and put it here, then we can write a to b gxi f of x dx as this quantity. Now if you look at here, this first term g1 xi xi y dash xi and here g2 xi xi y dash xi. So here since we already know that function gxi is continuous at x equal to xi, so these two will simply equal, and since it is plus sign here minus sign, so that these two will cancel here. Now again using the jump condition for Green function gxi, we can say that dever g2 xi dever x minus dever g1 xi dever x is going to give you 1 upon p x here. It is x equal to xi, right? So when you take this, this will be cancelled out and what you will get is your y of xi here. So what you will get here, let me write it here, you will get a to b z x xi f of x dx here. I am writing here p of xi and within bracket I am writing here g1 xi xi and y dash xi minus y xi g1 with respect to x here, so dever g1 by dever x and xi, and it is evaluated at x equal to xi here minus p of xi and g2 xi xi y dash xi minus y xi dever g2 dever x evaluated at x equal to xi. Now since g is continuous, so this will be cancelled out here, and using the jump condition it is p of xi and here it is written as dever g2 dever x at x equal to xi minus dever g1 dever x at x equal to xi, and this y xi is also there, so I am taking y xi out because it is common here. So this is basically 1 upon p xi, so I will get y of xi here. So y of xi is given by this formula. Now what we try to do here, we simply write y xi equal to a to b g xi f of x d of x. So it means I can write y of, say I can write down the same thing as a to b, and I can write it here, say I can write x as some t, so I can write it t xi and f of t d of t. So I can write this as y xi. Then I can change xi by x and I can write it here y of x is equal to a to b g of t x f of t dt. Now we already know that by looking at the structure of GTX has same as GXT, so I can write it here a to b g of xt f of t dt. So that is your y of x. So here we are using this fact that gxt is equal to gtx. So this says that we have that yx is defined by this formula. If we take our differential equation Ly equal to f and use the property of Green's function, then it will also satisfy this expression that is given as y of x equal to a to b gxi f of xi dxi. So that shows that if we know Green function for homogeneous boundary value problem, then with the help of this we can actually solve the non-homogeneous boundary value problem. Now let us look at the example based on this. So using Green function solve this non-homogeneous boundary condition. So here we have y double dash x minus yx equal to x. Boundary conditions are defined at y0 equal to y1 equal to 0. So if you look at, this is the operator, let us define this as our operator, and we can write down the general solution like this. And if you use the boundary condition here, y0 equal to y1 equal to 0, then we can get your both the condition both the constant a and b equal to 0. It means that we have only a trivial solution. So it means that we can now construct our Green function with the help of this general solution. So for that, using the method we have already discussed for construction of Green function for homogeneous boundary value problem, we can construct our Green function for this homogeneous boundary value problem, and it is given by this sin gxi equal to sin hyperbolic x sin hyperbolic xi minus 1 divided by sin hyperbolic 1 in this interval, and similarly we can define for in this interval. So our solution by the previous year, I can write yx equal to 0 to 1 gxi xi dx. Here if you look at, your fx is nothing but x here. So f of xi is going to be xi here. So now putting the value gxi here, which we have already calculated, we can write down like this, 0 to x and x to 1 like this. Now if here everything you can calculate, basically you can take out this sin hyperbolic x minus 1 upon sin hyperbolic 1, and in this interval you can take sin hyperbolic x divided by sin hyperbolic 1 out, and these are simple integral you can find out by integration by part, and you can say that this value is equal to this, and this integral x to 1 xi sin hyperbolic xi minus 1 dxi is equal to this quantity. And if we use these two integral and the previous expression for y of x, you can simplify this expression and you can say that the solution of this non-homogeneous boundary value problem is given by y of x is equal to sin hyperbolic x divided by sin hyperbolic 1 minus x. You can actually verify this also. So now let us look at the next result, which says that if this function phi of x is not a direct function of x, maybe it means that it is also involving the function unknown function y of x, then you can say that phi of x is written as f of x y of x. Then the solution we can write it y of x equal to a to b gxi f of xi y of xi dxi. So basically in this case, this is not a solution y of x which is given here, but the solution yx is given in terms of integral equation, or I can say that this differential equation along with these boundary condition is equivalent to the integral equation given here, and this is a Fredholm integral equation given here. So it means that in this case, when phi of x is not a function of x only, it is involving y of x, then this differential equation is converted into integral equation. So just look at one example here. Take very simple problem. Ly is y double dash fx yx y0 equal to y1 equal to 0. If you remember, we have already constructed a Green function for this problem, homogeneous problem. So for this y double dash equal to 0 with boundary condition y0 equal to y1 equal to 0, we have gxi equal to this, and with this we can write down yx equal to 0 to 1 gxi. Now here your phi x is fx yx, so I can write it yx equal to 0 to 1 gxi f of xi y of xi dxi. So here the solution of this boundary value non-homogeneous boundary value problem given in terms of Fredholm integral equation. So this is another use of Green function. Now let us use the same thing, but now we have a parameter involving that Ly is given as lambda y h of x, or you can say that your phi x is defined as h of x plus lambda y. So here we have defined phi of x equal to f of x y of x, and we can define this as lambda y plus h of x. So we can use the result which we have already described, and we can say that this problem along with boundary condition here, Ly you can take it like this, any linear operator and orthogonal linear operator we have taken here, and boundary condition this. Then this also can be converted into integral equation. So here if we take h of x equal to 0, we have a homogeneous boundary value problem, and the values for which the values of lambda for which we are getting a non-trivial solution, non-zero solution, we call those values of lambda as eigenvalues of the boundary value problem, and the corresponding non-trivial solution we call this as associated eigenfunctions. For example, we can have this particular result, that if we have Ly equal to 0 and Vky equal to 0, and for this if we have constructed our green function this, then the previous problem, this boundary value problem, Ly equal to lambda y plus hx with boundary condition this, the solution of that boundary value problem is given in terms of integral equation, this Fredholm integral equation, where f of x you can define as a to b gxi h of xi d of xi. So for this let us consider a simple example. So here we have y double dash plus lambda y equal to x. So here hx is equal to x here with the boundary condition y0 equal to y pi by 2 equal to 0, and we try to use green function to convert this differential equation along with boundary condition into a Fredholm integral equation. So for this particular problem y double dash equal to 0, we have so we just look at this problem as this. So here I will write it here, y double dash x equal to, I can write it x minus a lambda y, or you can write it like this, and we have y of 0 equal to y of pi by 2 equal to 0. So what we try to do is we have a corresponding homogeneous condition, homogeneous boundary value problem, y double dash 0 equal to 0, y double dash x equal to 0 with the condition y0 equal to 0 equal to y pi by 2, and here we can construct our green function which is given here as, if you remember, we have a formula for a green function like this. Now here coefficient of y double dash is simply 1, so I have not written coefficient of y double dash, so it is given by this. Now y1x, y2x you can find out as x. X is the solution of y double dash equal to 0 which satisfy the boundary condition given at x equal to 0, that is y0 equal to 0. Similarly x minus pi by 2 is a solution of y double dash equal to 0 which satisfy the boundary condition given at the end x equal to pi by 2. So we can say that y1x is equal to x and y2x is equal to x minus pi by 2. So with the help of this and the formula 30, we can write down the expression for gxi here. Now here Wronskian we can calculate easily, and we can see that it is nothing but pi by 2. So with the help of this we have gxi like this. Now it means that you can write it here, y of x equal to, now this is between 0 to pi by 2, 0 to pi by 2 gxi, and here we have x minus lambda y, we can say. Now this is what, this is f of xi here. So f of xi here is basically what, it will be xi minus lambda y of xi d of xi. So if you simplify, you will get lambda 0 to pi by 2 gxi y of xi d of xi plus 0 to pi by 2, and it is xi g of xi d of xi here. So that is y of x, and this once we know g of xi, you can actually calculate this. We have calculated here, and we can write it this quantity as sum f of x, and we can say our solution is given as y of x equal to fx minus okay, I have missed here minus, one minus I have missed here, yeah, minus, this is minus which I have missed here, so it is minus here. So here fx you can calculate as 0 to pi by 2 gxi xi dxi. So gxi is already given here, so let us calculate this f of x here. So between 0 to x, xi is we have between between xi between 0 to x means xi less than x, we have what? Xi less than x, we have this 2x by pi minus 1 into xi. So use this, here we have this expression, and between xi greater than x we can use this thing 2 xi by pi minus 1 x. So using this we can find out the value of these two integral, and it is coming out to be x cube by 6 minus pi square x by 24. This is not very difficult thing, it is simple integration, and with this value you have the solution of this problem yx equal to lambda 0 to pi by 2 gx xi y xi d xi, and this is your f of x given here. So it means that with the help of green function you can actually show the equivalence of a non-homogeneous boundary value problem of this particular type into a Fredholm integral equation. That what happened, I hope we have already discussed that we have Ly equal to f of x with the boundary condition that v1 say vk y equal to 0, and we have discussed this. But suppose in suppose these boundary conditions are not homogeneous, it is basically a non-homogeneous, then how we can write it? So we can say that suppose your these are not homogeneous, suppose we have these are some alpha k's, some values which is non-zero, then how we can handle here? So this we can handle in this two way. So what we try to do is we construct green function for this Ly equal to 0 with the condition that vky is simply 0, right? And we say that for this we have a green function g of xi, and we can find out the solution of the corresponding non-homogeneous boundary value problem as y of x equal to simply a to b. I'm assuming that x is lying between a to b, x is in between a to b. So here it is a to b g of xi f of xi d of xi. So if it is not alpha k is all or 0, your solution is given in this particular form. But suppose alpha k is simply non-zero, then what to do? Then what we try to do, we simply convert in this thing into two problem. So let me write it here, it is f of x here, okay. So this is the solution of what? This is the solution of Ly equal to f with the vk y equal to 0. Now what we try to do, let us look at this particular problem. We take Ly equal to 0 and vk y equal to say alpha k, and we can find out the solution here. And suppose the solution you can find out and say that it is f of x. Then the solution of the original problem is solution of this problem is basically your y equal to solution of this problem, call it y1, and solution, so it is given as y1 plus f of x here. So solution of the non-homogeneous problem with non-homogeneous boundary condition can also be given with the help of this, that solution of homogeneous problem you find out like this, and the solution of homogeneous problem but non-homogeneous condition, and say that solution is given by y equal to fx. So you covered y2 equal to fx, and solution of this non-homogeneous solution of this original problem I can give it like this, y equal to y1 plus y of 2, where y1 is given by this and y2 is given by this. So this is y equal to a to b g xi f of xi d of xi plus f of x here. You can verify this by simply operating your L on this, okay. So here we are using principle of superposition to truncate this problem into two parts, one with non-homogeneous equation with homogeneous boundary condition, and a homogeneous differential equation with non-homogeneous boundary condition, and you can easily solve this problem, and your solution of this problem is given by this. You can do this problem. Maybe we can discuss some problem in assignment here. So now here we close this lecture here, and we'll again discuss some more problem. Okay, thank you very much.